This is we have a visitor today which is going to tell us about things which are a little bit, I don't know, say controversial, different, or whatever you can name. Riccardo is support astronomer at the GTC. He is one of the support astronomers, has been working longer at the telescope since 2007. He will be the responsible, he was the responsible for Canary Cam, that you know now it's not working, but he will be installed again soon. So he's the responsible for the infrared instrument at the telescope. Besides that, Riccardo is an astronomer. He works on AGNs and cosmology in general, and he has his particular thing he likes a lot, which is this topic. I happened to coincide with Riccardo, one of the visits to the GTC, and he was extremely helpful and nice and whatever, because we had a visitor, and he was able to explain to them, which were not astronomers, his idea about this theory in a very simplistic or simple way, very nicely. Because of that, I asked him whether he would like to come here and tell us about that. He was very nice and said yes, so he's here, and he's going to tell us in a clear manner why he thinks this is important, why he thinks he has been ignored, I mean, anything he wants. So, Riccardo, thank you for coming.
Thank you. Okay, so let's start. This is going to be an introduction to the Modified Newtonian Dynamics. So, you probably already heard about it. This is a proposal basically to get rid of dark matter. Okay, dark matter is a big mystery. It's called dark because we know nothing about it. In particular, the dark matter has the, let's say, the problem, just to say a word, that it appears almost everywhere unexpectedly. You can have as much as you need to fit your data. You can assign to it any properties. So it's something that is not very satisfactory from the point of view of a scientific law or a scientific object. In particular, it has been noted since the time of the first proposal with MOND that dark matter starts to appear in galaxies and other astrophysical objects when and only when the acceleration of gravity falls below a certain value. Okay, and this value has been baptized as A0 with a lot of fantasy. And now we are in this situation in which every time in an object the acceleration goes below that value, that threshold, we need to introduce dark matter. It never occurs if the object has internal acceleration above this value, which is very strange because there should be no correlation between matter and dark matter, but we will investigate much more about this. So at present we have a lot of fine-tuning when we introduce dark matter, and we always place the exact amount of dark matter that we need. And also, because we are trying to modify Newtonian dynamics, of course we have to be careful, because we know that Newtonian dynamics works perfectly in the solar systems. But remember that this acceleration is way below the typical acceleration that we probe in our solar system. Just to remember you, the Earth is accelerated by the Sun with an acceleration which is of the order of 1 centimeter per second per second. Okay, so this is 10 to minus 8 centimeter. We are 8 order of magnitude below the acceleration that we usually probe in the solar system. And so the idea is simple. Newtonian dynamics breaks down below A0. And we need a different formula. Many formulas have been proposed, but only one has survived basically over time. Well, the first modification that was proposed was a modification on distance. So say, well, when the distance, because people were seeing dark matter in galaxy, then they say, well, when distances are about kiloparsecs, then we have to change the law. But distance has nothing to do with this. Okay, this is very important to remember. The only thing that is important is the acceleration, the strength of the gravitational field. Okay, so when the acceleration is stronger, I use the word strong for the Newtonian regime, not to confuse with the relativistic regime, which is very strong, let's say. So we have a strong Newton and weak MOND. Okay. When it's in strong field, the acceleration is Newtonian, the absolutely traditional formula. When the acceleration goes below A0 and the transition is pretty fast, the dependence is linear with distance, 1 over r. So this is basically the Newtonian formula, okay, the root square of the Newtonian formula multiplied by A0. Okay, so we retain the units. This is the root square of the product of two accelerations. So it's again an acceleration. And there is an interpolation function to join the two regimes. Of course, you don't have jumps. Well, this is not known at present. We only have an empirical formula that is derived by fitting a rotation curve. So, and you adjust with this formula, which is, as you can see, it goes with the square of the ratio of the acceleration. So it's pretty fast, and the change is pretty fast. Okay, so this was proposed in '83, and the important thing is that this object, this idea, introduced a new constant, this A0, which is constant. So you cannot play with it. It's fixed. It was derived very soon by Milgrom itself, studying rotation curve, which means that you take one galaxy, you fit the rotation curve. Okay, you take a galaxy, you put your spectrograph like this, you measure the velocity at different distances, and what you observe is that you have a curve like this one. Instead of the Keplerian fall off, you have a flattening of the rotational velocity. Okay, usually when you go far away from the nucleus, you still have few stars that can allow you to measure velocity, but all the mass is here, so you should have a perfectly Keplerian fall off, which is never observed. Okay, and this flattening is occurring always at A0. So Milgrom basically took a first few galaxies at the beginning, measured the value of A0, and fixed it to about 10 to minus 8. The most common value is 1.2 10 to minus 8, but we don't know it with that precision. And then you apply this idea, this framework to real data. Okay? Nothing about simulations. Okay, these are real data. So you take a galaxy, you measure a rotation curve. Look, it is really amazing. There are galaxies that have been studied specifically for deriving rotation curve with very high accuracy, and in particular using some tricks. You can use the hydrogen 21 centimeter emission lines or global clusters, planetary nebula to extend the rotation curve very far from the center. And we observe an amazing flattening of the velocity. Okay, so galaxy behaves this way, but galaxies do not behave like Kepler told us. And these are real data. There's nothing about simulation and so on. Okay, so you take your galaxy, your favorite galaxy, you build the rotation curve, and you try to describe it. So usually you have the stars, you have gas, and you have, if you want, dark matter or not. So this is the typical description of a rotation curve. You have the amount of gas that you measure. This is measured directly with the radio telescopes. You have the emission from stars. This contribution may be split in disk and bulge or whatever, okay, to refine the things, but it is stars, so you have to convert light to mass adopting a mass to light ratio. Mass to light ratio, a very important quantity here, talking about MOND. And then you add dark matter. Dark matter, but you can have as much as you need. This is it. It is a free parameter. You can actually have any shape for the distribution. The most favorite shape is the Navarro-Franken-White. I say, well, that it is used over and over, but with very little success. And the fact is that what you get is the amount of dark matter that is in that object and nothing else. You're not explaining the rotation curve. You just say, well, I observe this and I need this much dark matter, but nobody tells you that that is right or wrong, because you know nothing about dark matter. On the other hand, if you go to MOND, then you take your gas and stars and you get something like this one. A perfect fit of your data. And anytime a rotation curve has been improved in quality, the fit improved. We never observed a fit that it was okay when the data were, a bit fuzzy. No, nothing like that. The fit is perfect. And you can actually see, if you have good eyes, that there are two curves here, one dotted and one full line over there. That is the difference, assuming the two extremes for the distance of the galaxy. You have some few parameters, free parameters here. I mean, you have the distance, for instance, there's an error, and you have to adjust it. And that is the range of variation that you can expect. So the fit usually is very good. Then you can move to a lot of galaxies, and you always obtain a good fit. Again, this is always with MOND. So you have, in this case, you have three components because there is a bulge. So you have a disk, a bulge, and the gas. Over here you have only two, gas and stars. As you can see, the fit is usually very good. Now we have better fits for this one. This is an historic figure that I placed because it was one of the first one where they actually studied in detail MOND in 98. MOND was presented in 83. For about 10 years, nothing happened. And then in the 90s, thanks to, let's say, 2 or 3 persons working on it, they started publishing results, and now you see routinely appearing papers on this subject. So the law is this one, proportional with 1/r. And there are cases where you can achieve very amazing results. Here I introduced the two big families that there are among galaxies. Galaxies, you are used to know spirals, elliptical, you have dwarf, and so on. But galaxies also divided in two big families: the ice surface brightened galaxies, which are the regular galaxies we always talk about, like the Milky Way, M31, and so on. The beautiful spirals. And then we have the low surface brightened galaxy, which are galaxies where the stars are more far apart, and so the surface brightness in the sky is much lower. These are extremely important for MOND, the low surface brightness galaxy, because the acceleration is extremely small. So those galaxies are totally in MOND regime. Okay, so you can fit the rotation curve with no free parameter. In this case, they have just fitted the mass-light ratio to 1.9. And this galaxy is one of the most beautiful examples, NGC 1560, because the rotation curve is really amazing. You see, there is an increase of the velocity then it decreases, and then increases again. This is due to the fact that there is a minimum on the amount of gas. You can see the isophotes here. The isophotes are for the 21 centimeter emission lines. The hydrogen, you see there is a minimum here and here. Every time you have a minimum or whatever features in the mass distribution, in the light distribution you see, every time you see something like that, you have a similar feature in the rotation curve. Again, this is completely unexpected in dark matter because this object is expected to be totally embedded in a very heavy dark matter halo that should be able to cancel all features like that. And you can see here the solid line here is the fit with MOND. Dark matter is totally unable to describe that this structure because it is it's always a smooth halo that is added to the light distribution. So you cannot describe this one. There are several works where they try to fit that, but with no success. So now we can ask, but is MOND able to fit any rotation curve? After all, MOND was invented to do that. So one would think, well, it's easy, no? It's not easy at all because every single galaxy is a full test for MOND. It's not because you cannot change A0, and so every galaxy represents a test. It's like discovering a new planet tomorrow in the solar system, and you apply Newtonian gravity to that new planet. And if it does not agree, well, that would be the end of Newtonian dynamics, no? And so every galaxy is a new test for MOND. Well, you can see this nice plot here. This is a beautiful figure produced by De Block and Stacy McGaugh. This is a very smart guy, which has contributed most on this subject. Well, you can see that dark matter can fit this curve much better than MOND. So one can say, MOND fails to fit this one. This is just to show that if you take the gas and the star that you see and you cannot play around, there are no free parameters, so you end up with this curve, and that curve is fixed. You cannot modify it. On the other hand, if you add the stars and gas and you don't fit, well, you change the amount of dark matter, you change the shape of the halo, you can do whatever you want, and you fit basically anything. Indeed, this is a fake galaxy. This is not real data. This is the rotation curve of a galaxy with the photometry of another. And MOND, of course, fails because he cannot modify, he cannot adjust its curve. You give the light, and you end up with the velocity. There is no free parameters in the middle. But dark matter has a lot of freedom. Huh? So in this case, a failure is a good thing. Let's go on. So as I mentioned at the beginning, what is really disturbing for dark matter is that dark matter appears when and only when the acceleration goes below a certain threshold. And in this figure, we see this fact with high accuracy. Okay, so we have a sample of 153 galaxies. So we have 153 rotation curves. Every rotation curve has a number of points. Okay, so this has the galaxy. So we have 153 points here. Every galaxy is color coded to represent the amount of gas. So blue is full of gas. The small galaxy, you see these are the dwarf galaxies with low luminosity, 10 to the 8, 10 to the 9. And the surface brightness is also low. This is surface brightness, so luminosity for unit area. And this is the luminosity. And this one, on the other extreme, are the regular galaxy, the high surface brightness galaxy, which are dominated by stars and no gas. Can Okay, we have this trend, so we have 133 galaxies. Each curve have many points, so we end up with 2,693 points. And for every single point, we can calculate the acceleration due to the mass that we see within that radius. So we compute gm over r squared. And at the same time, because we have the velocity, we can compute the acceleration from velocity v squared over r, the circular acceleration. Okay? And these two, if there is no dark matter and everything is right, the two should agree. And indeed, they agree when the acceleration is strong. For instance, if you do this with global clusters, you end up with the same value. So the two accelerations agree. If you, on the other hand, if you move to galaxies, you see there is a systematic deviations. Guess what this line is? Well, of course, the line is MOND, and this is the Newtonian prediction, 1-to-1. But the problem is that the dark matter appears in any amount on this galaxy. These are points that comes from 153 different galaxies. So these points should move around here. And so you should see a cloud of points over there. On the other hand, we see a very well-defined relation. So in the dark matter scenario, this is a pure chance. I mean, this occurs for pure causality. Which, of course, has the probability that these do occur by chance is something like 10 to minus 20 or so. So let's move to one of the most intriguing things the galaxy do, which is the Tully-Fisher relation. The Tully-Fisher relation is a relation between the luminosity and the rotational velocity, this one, the asymptotic rotational velocity, to the fourth power. This is very strange because in Newtonian dynamics, you expect the velocity to appear with the square, not with the fourth power. Okay, so Tully-Fisher usually used as a distance indicator. It's a very precise. This is again is an historical version of the relation we have now. We will see in a moment much better version of the Tully-Fisher relation. We have a very similar relation for. This is for spiral. We have a similar relation for ellipticals, just replacing v with the velocity dispersion. So the luminosity proportion to the velocity dispersed to the fourth is called Faber-Jackson relation. These two relations are extremely important because they teach us a lot of things. But before we can understand the formula, just to remember that there are galaxies with high surface brightness, the regular ones, and galaxy with low surface brightness. Just the stretch in the figures is so that you can see that the outskirts of this galaxy are similar to the center of this one. So when we consider low surface brightness galaxy, we are in the same regime that we have in the periphery of high surface brightness galaxy. And a simple relation, so the total luminosity of an object, by definition, is the average surface brightness by the surface. Okay, very simple. You can adjust because it's not a circle, but nothing changed. So let's see. Can we explain the Newtonian dynamics? I mean, can we explain the Tully-Fisher with Newtonian dynamics? Well, it's pretty tricky because, as I said, we expect the velocity to be squared and not to the fourth power. But so we have these two relations. Okay, the luminosity expressed as a function of the surface brightness. So we take the square of the Newtonian relation to have v to the fourth. So we have v to the fourth. Get rid of the constants. So it's proportional to m squared over r squared. We take r squared from here, which is L divided by the surface brightness. So we have an L over here, surface brightness, and because we want luminosity to be proportional to v to the fourth, so we multiply and divide by the luminosity, and we get this nice relation where we see the Tully-Fisher. V to the fourth is proportional to the luminosity, provided that this quantity is constant. Okay? But this quantity is the product of two quantities, the mass to light ratio squared. Well, the mass to light ratio depends on the stellar population of the galaxy you are studying. So it is basically constant from galaxy to galaxy. There are variations, of course, but you will never find a stellar population with mass to light ratio 20. It simply doesn't exist, because when you mix a lot of stars, you always end up with a mass to light ratio which is of the order of 1, maybe 2, sometimes 3, but not 20 or 0.005, something like that. Okay, always of the order of 1. On the other hand, the average surface brightness of galaxy varies a lot, precisely because there are these two big families of galaxies in the universe, the high surface brightness and the low surface brightness. You can think about open cluster and globular clusters. They are the same thing, okay, on the scale of clusters. Good. So Newton tells us that basically because the m over L is basically constant from galaxy to galaxy, and there are two big families of surface brightness, so we should have two Tully-Fisher relations. One applying to high surface brightness galaxy, and another parallel for low surface brightness galaxies. These considerations were made by Milgrom itself in '83. There were no data at that time for low surface brightness galaxies. Okay, so this is a prediction. This is not an ad hoc explanation, find out a posteriori. But let's see what Milgrom wrote at that time. So he said, well, Tully-Fisher for MOND is a piece of cake. Okay, you have V squared over R equal to your relation, a Newtonian acceleration multiplied by I0 root square of it. Of course, the R disappear, and you have, we take the square because we want to get rid of the root square, and we want the Tully-Fisher relation, so V to the fourth is G, now it's equal, it's not proportional. Now it is equal, V to the fourth is equal to G, M, okay, we have M, A0, and then we multiply and divide by L, because we never observe mass, we only see light, so we have the Tully-Fisher relation, V to the fourth is equal to the luminosity, multiplied by constant, G and A0 are constant by definition, and the mass to light ratio is, as I said, almost constant moving from a galaxy to another, in particular moving from high surface brightness and low surface brightness. The mass to light ratio is the same. And so MOND predicted the Tully-Fisher relation to be universal with normalization GA0. So this means that if you know the velocity, you can know the mass. Or if you know the mass, you can know the velocity. Believe me or not? For instance, take the Milky Way. The sun orbital velocity is 220 kilometers per second. The mass is very difficult to know, but it's about 150 billion solar masses. And believe it or not, mGA0 to the to 1/4 is 221 kilometers per second. So if you know the velocity of the sun, you can know the mass of the Milky Way, just apply MOND law, exactly as you know the mass of the sun, knowing the velocity of the Earth. This is amazing. Think about the amount of work that is involved in deriving the mass of the Milky Way. It's really amazing that we can get the same number in a moment. Okay? This is true for any galaxy. You can play with all your favorite galaxy, and you will always end up with the right value. Okay, so about 10 years after Milgrom wrote these things, a group of investigators was able to obtain data for the low surface brightness galaxies and populate the Tully-Fisher relation. This, again, is an historic version of this figure, the first that appeared in 1998. And you can see that the Tully-Fisher is universal, is the same for all galaxies. Okay, velocity and luminosity. And the slope of this curve is 4. Okay, well, you can actually calculate from 1.8 to 2.4, there are 0.6. From minus 1.2 to 1.2, there are 2.4. 6 by 4 is 24, so the slope is exactly 4. Okay, let's go just one moment back here. You see, the Tully-Fisher is V to the 4 is equal to mass. The luminosity is only there because we cannot see the mass. But the relation is between velocity and mass. And this makes sense. The Tully-Fisher relation has no sense in Newtonian dynamics because the velocity cannot depend on the luminosity. Imagine you switch off half of the stars in a galaxy. What happened? Well, the dynamics of the galaxy does not change at all. But the luminosity will drop by 50%. So your galaxy will move off the Tully-Fisher relation. Okay? So the relation has to be between velocity and mass. And this is exactly what is shown in this modern plot of the Tully-Fisher relation. That now is called baryonic Tully-Fisher, because after realizing this, people started to include mass in the Tully-Fisher. Okay, so this is the traditional Tully-Fisher. We have the bright high surface brightness galaxy up here, dominated by stars. So because it is dominated by stars now and there is little gas, the luminosity is a good tracer of the mass, and you end up with a relation. But then when you move to dwarf galaxies where the gas start dominating, then you have little light compared to the mass, and your objects start moving away from the relation. As soon as you include the gas, the mass in gas, the relation is restored. Okay? And you have a perfect baryonic Tully-Fisher relation. Okay? Which has no explanation whatsoever in the dark matter scenario, because in the dark matter scenario, every galaxy here has its own amount of dark matter, which depends on how the stars are distributed, or, you know, many things. And all these points should move around and fill basically all the parameter space available. Well, nothing like that is observed. These are real data, not simulations. Remember, because it's so common nowadays to... Okay, so to be honest, I have to talk about the only aspect where MOND fails. Okay, MOND fails by a factor 2 when it is applied to cluster of galaxies. So you take a cluster of galaxies, you measure the velocity dispersion of the galaxy, you know how many galaxies there are, you know the luminosity of each galaxy, so you can compute the mass. Then you enter with the mass of the gas, because they emit X-rays, so you convert the X-ray luminosity into a mass, and so on. And you end up basically in Newton with this, with a discrepancy of about a factor 10. You said this is 10? Okay. And in MOND, you end up with a noisy distribution with, on average, is a factor or 2 off. Well, a factor or 2 in astrophysics is not too much, but this is, I mean, systematic and persistent. People are trying many ways to solve this, and there is no way. So we have a problem here. And well, you are all young astronomers, so it's for you to find a solution for the future. Well, I give you a suggestion. Say, there is a big difference when you study a cluster of galaxies compared to when you study a galaxy. The difference is that the clusters are very far away from us. And in order to convert observed quantity to physical quantities, in particular the size of your cluster, you need to adopt a cosmology. Okay, so you adopt the lambda CDM cosmology, but the lambda CDM cosmology uses dark matter. The lambda CDM cosmology is certainly wrong if MOND is correct. And because you are trying to demonstrate that MOND is correct, you cannot investigate these objects using lambda CDM. It's a nonsense. So you need a cosmology without dark matter. And then you apply that cosmology and you see if MOND works. Okay? So for the future, keep in mind this. Okay? Once we will have the correct cosmology, then this one will fit. At present, there is no way. Let's see. Now, I just talked about what MOND is not able to do. Now we see what dark matter is not able to do. One big problem of dark matter is that it can make no prediction. Okay? You have studied a trillion of galaxies, then you go to galaxy number trillion plus one, and you are not able to say what you are going to find. This is from the point of view of a scientific theory is useless. Okay? To have dark matter or not is the same, because you are not able to make prediction. For instance, ultra-compact dwarf galaxies is the last entry in the realm of galaxies. Astronomers, they like to introduce new classes of objects. And so these are galaxies quite interesting. They were discovered studying the Coma cluster and the Virgo cluster. Now they find them everywhere. Are a compact object that looks like stars in regular ground-based images. And nobody ever took a spectrum of those targets because I'm studying a cluster and I'm not taking the spectrum of a star because it's just a waste of time. But these guys had a new spectrograph, a new multi-object spectrograph, able to take, I don't know, 1,000 spectrum at a time. So they say, well, we take the spectrum of everything that is in the field, including stars. A pure waste of time. But nevertheless, they find a new class of object that looks like a star, but they had the redshift of the cluster. So they could not be stars. They had to be, heavy object. From the luminosity, you immediately compute a mass of the order of 10 to the 8 solar masses. Okay? Unfortunately, in order to pack many spectra in your CCD, the resolution was limited. So they were able to measure the velocity, which means the redshift of the object, but not the velocity dispersion. So they didn't know the mass, the dynamical mass. They know the luminous mass because they see the target, but they didn't know the dynamical mass. And so in this paper, they say, well, we know that these are small because they are point-like. So these are small. So are dwarf galaxies because of the luminosity. And so usually dwarf galaxies are full of dark matter with mass-to-light ratio of the order of 100 or more. There are galaxies that have an immensely large mass-to-light ratio of the 400 or so. It's ridiculous. Okay, so they were expecting a lot of dark matter. Okay? And so they said, well, we will reobserve this. On the other hand, in MOND, you can make prediction in MOND. Okay? You don't have to say, well, because the other galaxy behave this way, so perhaps this new one will behave the same way. No, in MOND you make prediction. And all you need to know to understand this object is one word. The only word you need to know is this one, compact. Compact means the stars are close by and gravity is strong. So everything is Newtonian in these objects. This object will never show dark matter because Newtonian gravity works perfectly for them. And when you compare acceleration from luminosity to acceleration from velocity, you end up with the same value. And you don't need dark matter. You just need one word, compact. Problem solved. Okay, so there is no need of dark matter in this object. Dark matter will not be found. Actually, you see what they wrote on the Nature paper. Nature is famous for publishing this kind of paper where you always present something new. So we plan to reobserve this object at Eiger spectral resolution from the ground and Eiger spatial resolution with HST in order to be sensitive to mass-to-light ratio of 100. This was their expectation, okay, for this kind of objects, because dwarf galaxies do have a lot of dark matter. It's trivial, no? And so, and this also will allow us to distinguish from globular clusters, okay, because globular clusters usually don't have dark matter. Well, of course, they found no dark matter, and so another big paper saying, amazing, we have not found dark matter in this object, this is a big discovery, and blah, blah, blah. This is no big discovery at all. Simply, they found a mass-to-light ratio which is fully consistent with the stellar population because everything is Newtonian, because the object is compact. Okay? And the accepted explanation, which is even more unbelievable, the accepted explanation is the one called galaxy trashing. So this galaxy used to have a lot of dark matter, but they lost it. They lost it they used this word, in the harsh environment of a cluster of a galaxy, where galaxies, they compete each other, trying to destroy each other constantly. Well, we will see in a moment that nothing like that happened. Okay, so basically, they found no dark matter. These are the objects. They are basically close to global clusters. If you look carefully, okay, this is an ultra compact dwarf. This is a dwarf galaxy where you see an halo, okay, and if you measure the velocity here, you need a lot of dark matter to explain the velocity because the stars here move very, very fast. And the nucleus of this, which is this one, is similar to the ultra compact dwarf. So the idea is that in this terrible environment, which is the environment of a cluster of galaxies, the galaxy lost everything except the nucleus that was the most strongly attracted by gravity. We will see that nothing like that happening in cluster of galaxies, because simply a galaxy like this one may sit just on the side of a galaxy with yellow, and the two have lived all the time in the same cluster. So, so you don't expect the galaxy to lose that easily their material. And so another interesting example of the total inability of dark matter to make a prediction is this one. So up to the year 2018, we have studied quite a number of galaxies. And so you should expect to be able to know what is going to happen when we study a new galaxy. But no, we are not able. So let's see what Van Dokkum et al. Wrote in an interesting paper in Nature again this year. So studies of galaxy surveys in the context of cold dark matter paradigm have shown that the mass of the dark matter halo and the total stellar mass are coupled through a function that varies smoothly with mass. the figures that I showed at the beginning. Okay? So he knows it. But of course, he's not able to accept it because he should accept MOND. And so he is desperate for finding a galaxy with no dark matter, because if we can find a galaxy with no dark matter, one is enough. If you can find a galaxy with no dark matter, MOND is gone. Okay? Provided that the acceleration is below A0. Don't confuse the... Okay? So, they studied a low surface brightness galaxy. And they studied this one because there were a number of objects, I think these two are two of them, that are similar to globular clusters. So they say, look, there are globular clusters there. They were able to identify 11 globular clusters. They measured the velocity dispersion of the clusters. And so they said, this is the velocity dispersion of the galaxy. Then you take the luminosity, the velocity dispersion, and you compare the two accelerations. And they end up with the same value. So they said, this galaxy does not contain dark matter. So we have a galaxy, NGC 1052, demonstrates that the dark matter is not always coupled with baryonic matter on galactic scale. So that figure that I showed before is wrong. And automatically, MOND is wrong. Okay, and any alternative to gravity is wrong. This was the bet of these guys. Okay, and the bet of nature that is obviously clearly supporting this point of view. Well, this result was soon it was criticized. Also, I posted a critic to this on AstroPH. It was demolished by our colleague Trujillo, and with a very, very nice paper, very well done. I hope to see him here, but it's not. Well, basically, what was wrong in the analysis? There are a lot of things that are unmentionable because the paper is pure crap. But nevertheless, it was accepted in Nature. Okay, because it was going against modified gravity theories. If it were the other way around, it would never be accepted, but never ever. Not in a million years. Okay, so what was wrong was the distance of the galaxy. The galaxy was basically at half the distance where it was claimed to be. Actually, Van Dokkum and collaborators associated this galaxy to NGC 1052, which is not the name of the galaxy. Okay, this is nearby over here, a large spiral galaxy that is studied in great detail. We know the distance. And they say, well, projected on the sky, this one was the nearest to the dwarf galaxy. And you see, this galaxy it is inside a cluster. And it is able to retain all its stars, even though the gravitational field is tiny compared to the gravitational field of an ultra-compact galaxy. But the ultra-compact galaxy, because they needed it, has to lose its dark matter. But this one can retain it. Okay? Well, in this case, they were claiming that there is no dark matter, but it's wrong, because it is actually associated with another galaxy that is sitting a bit far away than NGC 1052. Okay, but when you move everything closer, actually the nearest galaxy is the one that appears farther. And you end up that being smaller, this galaxy in physical units is smaller, so V squared over R, the R is smaller, so V squared over R gives you a larger acceleration. And so you need dark matter to explain, because the light is not changed. Okay, so you end up with a galaxy that does contain dark matter, as expected, in MOND. MOND would say, no, this galaxy, being a low surface gravity, has to have dark matter. So it must show deviation from Newtonian gravity. When you say dark matter in the context of MOND, it means only a deviation from Newtonian gravity, because dark matter doesn't exist in this context. Okay, so we learn an important lesson from this galaxy. Okay, we import the lesson that the dark matter paradigm is unable to make any prediction and is useless as a scientific theory. Okay, keep in mind before you decide to devote your entire career to looking for dark matter. Okay, let's move to other class of objects. Okay, there are spiral and elliptical galaxies. Elliptical galaxies are very nice because they are strongly concentrated at the center. I'm way too long in time because I can go on for 2 hours. I go quickly. So just to show, elliptical galaxies do show the same effect. So you have the velocity dispersion, maximum at the center, then it gets flat. And you see if you have a bulge-dominated galaxy like this one, you see the rotation curve of the disk. This is the bulge and the disk, and they behave exactly the same way. This is another example. You see the velocity flattens at the same value, even though the disk and the bulge can be dynamically distinct structures, but they have to follow the same gravitational field. So for elliptical galaxy, as I said, using the trick of utilizing planetary nebula, you can actually study the velocity dispersion very far away, and even farther if you use globular clusters. And you find this very same behavior. Over here, the acceleration is A0, okay? You move from 2 different families, but the acceleration is the same. And so, just to I may conclude here, if you go and say, okay, we know the MOND works for galaxies, what happens if we move to another kind of objects? In particular, what happens if we move to globular clusters? Well, globular clusters, if you go far enough from the center, okay, you see the flattening of the velocity dispersion over here. Okay, this is the first study of this kind. It was my idea. Okay, in 2003 we did this study with the VLT. We were able to study 75 stars. Members of the cluster are very far away from the clusters, and the acceleration, well, the velocity dispersion became flat. There was no very good agreement though, but then Solima, another colleague of us, he decided to investigate much more this cluster. They presented radar velocity for many stars, and you can see how the dispersion of the objects, the velocities, it becomes constant. So using the new data and the old data together, you get a better fit and a much better result. This has been then extended to a number of globular clusters, and they all start to deviate for the same value. This is MOND and this is Kepler. Okay, so you see how points start to cluster to on the MOND prediction in object that should not contain dark matter. Remember, these are globular clusters. These are not galaxies. And they always teach to us, oh, globular clusters don't have dark matter. Why? Well, because we don't need it. Okay? And so on. And just to end up, again, low surface brightness galaxy do have a very weird velocity dispersion profile because it is completely flat. So the combination between of the mass distribution and the acceleration ends up with this very weird relation. And if you apply the same to a low surface brightness globular cluster, because they do exist, okay, you can see through this cluster, you see the opening, then you end up with a very similar velocity dispersion. Okay, and I stop here because I see that people want to go to lunch.
Thanks to Riccardo. Is there any question, comments?
I think that the tone, the way you're presenting things is not quite the proper one. So I think the community is eager to know about other alternative theories and to question whatever we have, but you're presenting things in a very biased way. So when you say that we know nothing about dark matter or there is no theoretical motivation for that, that is simply not true. And I think it's important that we say that to the students. I mean, I don't know which kind of physical motivation you have presented here to modify gravity. You have just presented a new fit on other scales, and you managed to fit some rotational curves. That's good with MOND. It's doing a good job on that, but it's simply not. It's not satisfying as a theory. When we work with dark matter, we have theoretical motivations for particles. We know about the Lagrangian, or the symmetry in the Lagrangian of the electrodynamics, and that could motivate an axion. We know about supersymmetries. Neutrinos were discovered by Pauli without seeing them.
Yeah,
the Higgs boson.
You're making another talk.
Was like
I understand your point.
We knew before the day before seeing the Higgs boson. We knew that.
You listen thousands of times over and over.
No.
This story about dark matter.
Excuse me.
And so what
dark matter in the 80s CMB was not observed simply because the fluctuations in the CMB were not that strong because that could be explained with a component with gravitational wells produced by dark matter, and it happened that the prediction was 2 orders of magnitude, and until the 90s, when the fluctuations were of 10 to the minus 5, they were not observed. We are constantly analyzing galaxy surveys. That's where I am working on, and we are using dark matter models, which I'm happy to throw away as yesterday's newspaper if a better theory comes, but it's simply a very local theory, and I'm telling you, we are computing the dynamics of galaxies based on the fact that it's dominated by a larger amount of matter which we cannot directly observe, and it happens that we are perfectly predicting the redshift space distortions, the peculiar motions of the galaxies. So this is work which is happening now. Another work I would like to mention is the phase space structure formation calculations, which are now feasible, where it's not about modeling dark matter as with some test particles, but really as a continuous phase space, if it's true that those are so many particles which form like a continuum, and the Navarro-Franken-White profile is being predicted now from those calculations. Okay, thank you.
Well, you know...
Just a comment. I think this is clearly a very... I am sure that the students have they know different things, and I also understand that our speaker or guest is telling us the thing he has been working on particular things. He's clearly very much in favor of MOND, and he's trying to make his case. Obviously, you have shown very interesting results, which maybe these are the things we could comment on. The results he has shown, the plots he has presented, and probably
it's very important to say that these are real data. These are not simulation. I'm not looking on the hard disk of my computer. I'm taking the telescope and looking at what galaxies do. Okay, and galaxies do not behave the way he's saying. This is it.
Well, in any case, what is clear that maybe, because any speech has a little bit of exaggeration in the way that the premises are presented. Obviously, he's very fond of that. But I would like to, if you don't mind, to center the discussion on the number, the result, the plot he has shown, because otherwise it's quite...
Because galaxies behave that way. The physical motivation is that one. Take a galaxy, build your rotation curve, and it deviates from Newtonian dynamics. So you need another formula, and that is the physical motivation. Exactly like Newton at his time decided that the gravity should follow a certain law because it was the law that worked. That's it. You are free to do it. After 10 minutes, you will find that your theory doesn't work.
Okay, let's, Claudio?
I mean, several proposals have been made. And there are, for instance, there is another idea called MOG for modified gravity that works rather well. It's more complicated than MOND, way more complicated, but it works rather well. We have a relativistic version of MOND called Tevez. So there are things if you want to look, and the idea is that when you leave, it's like if I were going in a church and said, well, look, I demonstrated that God doesn't exist. So you expect that these guys go home and start, investigating on what I just said. So you should do the same. Go home and try to demonstrate the MOND is crap, because it is pure crap. Go home and write a nice paper where you can demonstrate, look, these are the data, this is MOND, it doesn't work. That's it.
Well, there are some observations that cannot be explained by MOND.
The cluster?
Clusters.
That is the only case, and I give you a suggestion.
Gravitational lensing.
No, gravitational lensing never occurs in MOND regime.
Exactly, but we observe it.
Yes, you observe, it works.
Okay, but my question was more general. My question was more general.
Indeed, I think I have no, well.
So you mentioned Tevez. I read about Tevez, and Tevez does some job on very large scales, but not cannot explain the CMB without including some small fraction of matter or extra dark matter. Call it a dark matter, call it an effect on the gravitation, a potential well, whatever. Okay, so it doesn't.
Yeah,
but
my question is you are basically asking too much. No theory has ever explained everything.
No, wait.
Okay, we are at the beginning.
Sorry.
Read this one. What is the?
You cannot stop me before I finish.
Okay, go ahead.
So the thing is that you say that I'm asking too much to Newtonian dynamics, but the lambda CDM fits all these things. So it does much more than MOND. So I'm asking, is there any, my question was very general. How do you explain galaxy formation within the MOND theory, which I don't think is a theory, is a fit. It's far from being a theory, okay? But how do you explain galaxy formation?
Galaxy formation, you can explain exactly like in lambda CDM, in the lambda CDM scenario. There is a nice paper out there by Stacy McGaugh where he can describe the fluctuation of the CMB without dark matter. But of course, well, but as I said, wait a minute. The fact that you ask, MOND is not able to explain things that we see at cosmological scales. Okay, so MOND doesn't agree with cosmology, and your conclusion is that then MOND is wrong. That is not correct. A law of physics doesn't have to agree with cosmology. It's cosmology that has to agree with the law of physics. And you build your cosmology according to the law of physics. So if one day one guy comes and say, guys, we were wrong, the law of gravity is this other one, then you change cosmology. It's as simple as that. No. There is the large scale structure are data observed, of course. Yeah, but I mean, what are you explaining with the large scale structure, with the fluctuation? What are you explaining? Nothing. You just introduced dark energy, which is even darker than dark matter, and you said, "Oh, we have understand everything." Remember that 30 years ago, people were trying to measure the deceleration parameter. They assign a name of that parameter, unfortunate name, called deceleration. Okay? It's the Q0 that appears in those formulas. Deceleration parameter. And they found out that it was an acceleration. And they said, we have understand everything. We have understood everything. So they were expecting the apple to go down, and then it went up, and Newton said, we have understand everything. Dark energy. Well, if you are happy with that, go ahead.
Yes, can we go to the slide where there's a fake galaxy which MOND didn't fit and dark matter apparently did?
No,
the fake galaxy with...
This one. I lost the window. Yeah, I know, number 5, but it's not starting. I don't know the... Well, what is your question? Is what is it? I don't see the mouse.
It's not like 5.
Yeah, okay. Yeah?
Yeah, it's lower now.
Okay, it's this one, no?
No, it was a different one. It was...
This one or the previous, the following?
No, the one with the fake galaxy.
Okay.
The one that... There one.
This one.
So my question is, in the MOND fit, are the contribution of gas and stars derived from the luminosity in the data?
Yes, but the luminosity is for one galaxy, and the rotation curve is for another.
What I mean is, why are they different contributions in the fit to dark matter? If they were derived from the luminosity?
Because you can play with the mass to light ratio. So the author here, they just increased as much as they could the mass to light ratio in the MOND fit in order to have let's say, an acceptable fit, because it doesn't fit at all. I mean, if you use the correct mass to light ratio for the stellar population that you see, the rotation curve is way below, like in the case of dark matter. Okay, so they said, to be fair, we use the free parameters for MOND, the mass to light ratio, which is not 100% defined. And then you do the same with in the dark matter scenario. But the dark matter scenario, okay, the ideal was to increase a lot the amount of dark matter and reduce the the contribution from stars and gas.
So are the mass to light ratios?
But I mean, it's trivial. You simply have more free parameters with the only thing that this figure wants to say is that with dark matter you have free parameters and you have the ideal free parameter, which is dark matter, because you can have as much as you can. You have no constraints on it. If in a galaxy you need 10 times dark matter than luminous matter, it's fine. If you need 20 times, it's fine again. If you need 5 times, it's okay. Because you don't know. Any galaxy is different.
Yeah, but you can constrain things instead of leaving so many free parameters. So, I mean, like, this might be not
the fit is
criticism.
Also, the fit is not perfect. With MOND, you could fit those nice bumps.
Yeah, but what I mean is, this would not be a criticism of dark matter, but of the way this fit is performed. Because you are modifying the mass to light ratios too. And those could be derived.
Again, the mass to light ratio is linked to the stellar population. The stellar population is known with an uncertainty. So you can play around with the uncertainty and change your mass to light ratio.
Yeah, but
Because you want to fit something, then you say, well, as much as I can increase the mass to light ratio, okay, up to here, fine. Then you move it up to there, and you see what fit you end up, and you end up with this one. On this case, you can move the mass to light ratio in the other direction because you have uncertainties, and increase the dark matter, and you end up with a good fit. And that would be a perfectly acceptable explanation of that rotation curve in the dark matter scenario.
Yeah. Okay.
It's a hot topic, and there's always a heated debate when people are talking about MOND. And, I mean, it can get really, really awful. I have a beautiful test case for MOND, and many people actually have considered that. I wonder, because you did not present this, and I would have put this first slide, the bullet cluster. It's a beautiful case where you have the gravitational lensing telling you the distribution of matter, and then you have the gas in the X-rays, which is actually sloshing back and forth with the Bowshot. MOND, how does it explain the bullet cluster?
No, the bullet cluster is a tricky object. It's not easy to explain with MOND, and basically you have to assume that what we see, the gas and the cluster and so on, all projected along the line of sky, are not what we claim they are, basically. Also, again, because this Stacy McGo is publishing everywhere. I mean, there is a nice paper by Stacy where they discuss specifically this subject, and you can find an explanation there. Mm-hmm.
So,
well,
yeah. Yeah, so I would have so many questions, many comments, and so on, but I would try to move the discussion to a little bit different point of view. So the rotation curves, if I understand well, MOND would predict that they will stay flat forever, right?
Yeah.
So if we find examples of rotation curves that far away start to decline, that do you think that would be a good test against MOND?
Yeah. Okay. But no one ever found it, and I assure you that they are looking very.
Because, for example, this kind of thing would fit very well.
They are trying very hard to find the initial drop off of the rotation curve. They never find it.
Yeah, but it's a matter of time, because I mean data would increase, and I mean it's a matter of time to go farther away. I don't know whether this would decline or not. But definitely that would fit well with dark matter scenario, but not with the MOND, if you agree, no?
Okay. Necessarily, if you start seeing the decrease.
Okay, so that's something that is within the next year, I would think.
Yeah, but MOND makes a lot of prediction and has no freedom. So whatever evidence you find against it, I was about to mention, but there was no time, that the next step, we move to global clusters. The next step is to move to double stars. Double stars, if they are really far away, they enter the MOND regime. If you study the orbital motion of a double star with a separation larger than 7,000 AU for a solar mass, you will enter in MOND. But it's up to you to improve things. I mean, when Bohr introduced his model of the atoms, he said, the atom works this way because I say so. Okay? The electron doesn't emit because I say it doesn't emit, it's stable, and blah, blah, blah. Okay. At the beginning, it was crazy ideas. Einstein went to the grave, convinced that there was a better explanation than that. But those ideas became quantum mechanics that we have nowadays. And no one complains about quantum mechanics. Everybody's happy. So we have MOND now. Is a the embryo of a theory that eventually will explain the behavior of gravity as in the universe. Thank you for inviting me. Thank you.